Hello, everyone. I am Professor Hua from the Communication Engineering Teaching and Research section at Wuzhou University, and welcome you to this mini lecture. Today we continue with Chapter 4, Frequency Domain Analysis of Signals, focusing on Section 2, Properties of the Fourier series of continuous periodic signals. In the previous lecture, we discussed the exponential form and the trigonometric form of the Fourier series expansions for continuous periodic signals, as well as how to compute their coefficients. Beyond these topics, the Fourier series also involves the properties of the Fourier series and the spectrum of the Fourier series. In this lecture, we will study these aspects in detail. Let's begin with the first topic of today's lecture, the fundamental properties of the Fourier series. 1. Linearity property. The Fourier series expansion is a linear operation. It satisfies both homogeneity and additivity. The precise mathematical expressions are given below. 2. Time shift property. If a continuous periodic signal is delayed in the time domain by t0, then its Fourier series coefficients are modified accordingly. Specifically, each coefficient Cn is multiplied by a complex exponential term that depends on t0, as shown in the formula. 3. Convolution property. If f1t and f2t are both periodic signals with the same period t, then the Fourier series coefficients of their periodic convolution in the time domain are equal to the product of their respective Fourier coefficients, multiplied by the period t. 4. Differentiation property. The Fourier coefficients corresponding to the derivative of f of t become the original coefficients Cn multiplied by the imaginary unit in n times omega 0. 5. Symmetry property. This property applies mainly to the case where f of t is a real signal. As we discussed earlier, for a real signal, the Fourier coefficients Cn exhibit conjugate symmetry. From this property, it can be shown that the magnitude of Cn is evenly symmetric, and the principal value of the phase angle phi is oddly symmetric. Now let's move on to the second topic of today's lecture, the spectral analysis of continuous periodic signals. First, let's recall the concept of spectrum. A periodic signal f of t can be decomposed into a sum of complex exponential signals at different frequencies. Different time domain signals differ only in their Fourier series coefficient Cn. Therefore, by studying the coefficient Cn, we can investigate the characteristics of the signal. Since Cn is a function of frequency, it describes how the amplitude and phase of the sinusoidal harmonics that make up the signal vary with frequency. This function is called the spectrum function. Next, let's discuss how to represent the spectrum. From the expression of Cn, and knowing that Cn is complex, we can express it in terms of its magnitude and principal phase angle, as shown in the formula. The magnitude of Cn describes the amplitude frequency characteristic, also called the amplitude spectrum. The phase angle phi describes the phase characteristic, also called the phase spectrum. If f of t is a real signal, then the magnitude of Cn is evenly symmetric and the phase angle phi is oddly symmetric. Now, let's take the Fourier series coefficient Cn of the periodic rectangular pulse signal we studied earlier as an example, and look at its spectrum diagram, as shown in the diagram. From the diagram, we can observe some important properties of the spectrum of continuous time periodic signals. Let's highlight 3 aspects. The first property is the discrete nature of the spectrum. The spectrum of a periodic signal consists of spectral lines spaced by omega 0. If the signal period t is large, then omega 0 is small, and the spectral lines are densely spaced. Conversely, if t is small, the spectral lines are more widely spaced. The second property is the amplitude decay characteristic. From the diagram, we can see that as the harmonic frequency increases for a periodic signal, the amplitude of the spectrum gradually decreases and eventually approaches zero. If the time domain waveform of the signal is relatively smooth, the higher order harmonic components are fewer, and the amplitude spectrum decays more rapidly. Conversely, if the time domain waveform contains more abrupt changes, the higher order harmonic components are richer, and the amplitude spectrum decays more slowly. The third property of the spectrum concerns the effective bandwidth of the signal. As shown in the figure, the frequency range from 0 to 2 pi over t is defined as the effective bandwidth of the periodic rectangular pulse signal, or simply the effective bandwidth, denoted by omega b. The exact calculation is given in the formula. It is important to note that the effective bandwidth of a signal is inversely proportional to its duration in the time domain. The concept of effective bandwidth has practical engineering significance in signal processing. If the harmonic components outside the effective bandwidth are lost, the signal is not significantly affected. When a signal passes through a system, the effective bandwidths of both the signal and the system must be matched. In other words, the effective bandwidth is not only a property of the signal itself, but also a crucial consideration in system design. Next, let's briefly introduce the third topic of today's lecture, the power spectrum of continuous periodic signals. From what we studied in Chapter 1, we know that periodic signals belong to the category of power signals. Their power can be calculated directly in the time domain. After we learn this chapter, based on the principle of energy conservation, the power can equivalently be computed in the frequency domain. An important theorem in signal processing is Parseval's theorem, which establishes the conservation of energy between the time domain and the frequency domain. For periodic signals, the theorem states, time domain calculation. The average power of the signal can be obtained through time domain integration, that is, by averaging the instantaneous power of the signal over one period. Frequency domain calculation. The same average power can also be obtained by summing up the squared magnitudes of all harmonic components in a frequency domain. The distribution of the squared magnitude of Cn with respect to n times omega 0 is referred to as the power spectrum of a periodic signal, or simply the power spectrum. In summary, Parseval's theorem reveals how a signal's power is distributed in the frequency domain. The total power is simply the linear superposition of the powers of all its frequency components, which directly reflects the principle of energy conservation. Finally, let's discuss the last topic of today's lecture, the Gibbs phenomenon. Please first observe the four waveform diagrams below. Each diagram shows a continuous periodic rectangular pulse signal f of t approximated in the time domain using its Fourier series with different values of n. From these diagrams, we can see that as n increases, the waveform becomes closer to the actual signal. However, you will also notice a persistent issue: oscillations at the discontinuities. These oscillations do not disappear even as n increases. This phenomenon was explained by the American physical chemist Gibbs, and it is now known as the Gibbs phenomenon, referring to the persistent oscillations at discontinuities that do not disappear. Specifically, the Gibbs phenomenon occurs when a signal with discontinuities is approximated using a finite number of harmonic components. At the points of discontinuity, overshoots appear. The peak value of these overshoots does not decrease as more harmonic components are added and is approximately 9% of the jump in signal value. The main reason for the Gibbs phenomenon is that the abrupt jumps in the time domain signal break the convergence of the Fourier series, resulting in non-uniform convergence at the discontinuities. Please reflect on today's lecture and complete the following homework exercises to consolidate the concepts learned and deepen your understanding. That concludes today's mini lecture. See you next time.